Hello guys, in this video we will consider an application of triple integral. In order to do that, we'll solve this problem. Let E be a solid bounded by a cylinder of equation y squared plus a z squared equals 9 and by the plane x equals 0, y equals 3x and z equals 0 in the first octant. Consider that the density function is a constant defined as rho of x, y, and z equals k, where k is a constant. And the question asks to us find the value of the mass of the solid E. So let's begin. Firstly, we'll consider the cylinder of equation y squared plus z squared equals 9. Let's isolate the z variable in this equation. To do that, we just have to send the y squared to the right side of this equation and take the square root in the both sides of the equation. So we have two equations with z isolate in the left side. The equation with the plus sign will represent the upper side of the cylinder in navy blue. On the other hand, the equation with the minus signs will represent the lower side of the cylinder in orange color. Note if we consider the cross-section parallels to y and z plane, we got circles with radius equals 3. We have 3 more planes to consider in this question. Let's draw the plane z equals 0. Once every point that have the third coordinate z equals 0 actually lies in the plane x and y, we have that the z equals 0 is the same that the plane x and y. We draw this plane using the purple color, and as we see by this figure, this plane cuts the cylinder in half. Once the question asks us to consider just the point in the first octant, that is x, y, and z are greater or equal than 0, we can get rid of the lower part of the cylinder. The next plane that we have to consider is x equals 0. This one is the same of the plane zy. We represent this plane using the light blue color right here, and we pass through the cylinder just as shown in this figure. Finally, we will consider the plane y equals 3x, and if we focus just in the intersection of this plane with the yx plane, we got the straight line of equation y equals 3x in red color. Consider all the other points that has a z coordinates different of 0. We got the plane represented in the red color in this figure right here. To get the solid E, we have to analyze all the intersections among the cylinder and the planes in the first octant. If we focus in those intersections, we got this isolate region as shown in this figure, that will provide the integration limit to calculate the mass of the solid. Once the maximum value that y assumed is 3, the intersection between the solid E and the straight line y equals 3x must be the point I of coordinates 1, 3, and 0. Once if I put this value 3 in the variable y, I will conclude that x must be equals 1. The intersection of the solid E with the xy plane is highlighted in blue color right here. From this figure, we can conclude that x varies from 0 to 1. Once the variation of y is from this line, y equals 3x, to the line y equals 3. look once more to the 3D figure of the solid E, we can conclude that z varies from z equals 0 to the upper side of the cylinder that have the equation plus square root of 9 minus y squared. Thus, we can conclude that our solid E can be determined as E is equal all the points x, y, and z in R3 such that x varies from 0 to 1 and the variation of y is from 3x to 3 and the variation of the variable z is from 0 to square root of 9 minus y squared. The mass of the solid E is defined as the triple integral in E of the density function rho of x, y, and z dv. Well, substituting this integration limit in this integral right here, we can conclude that the mass m can be represented as the integral from 0 to 1 of the integral from 3x to 3 of the integral from 0 to square root of 9 minus y squared. The density function is the constant k. Once k is constant, we can leave it outside of the integrals. The first integral, notice that it's the integral of dz. The integral of dz is just z, and z varies from this integral limit to this one. So the result of the first integral is just the square root of 9 minus y squared. At this point, we call this integral right here of 1 and we'll perform the calculus of this indefinite integral. We begin isolating the 9 outside of the brackets right here, and we'll call y squared over 9 as y over 3 squared. At this time, we'll perform this substitution right here. We call y over 3 as a sine of theta. If we apply derivative in both sides of this equation, we have in the left side dy over 3 and in the right side cosine of theta d theta. Therefore, dy will be equals 3 times cosine of theta d theta. So we will substitute y over 3 as sine, so we have sine squared of theta, and the dy will write as 3 times cosine of theta d theta. This 3 right here will multiply the 3 outside of the integral, so we have a 9 outside of the integral times this 1 minus sine squared of theta by the fundamental law of trigonometry could be written as cosine squared of theta. So this square root of cosine squared of theta times cosine of theta will be just cosine squared of theta, and we will apply this substitution right here. We can write cosine squared of theta as 1 plus cosine of 2 theta over 2, and this denominator 2 goes outside of the integral, and we'll split in two integrals right here. The first integral is just the integral of d theta, which will be equals theta, and the second one, it's an easy integral to perform too. It's the integral of cosine of 2 theta d theta. It will be 1 over 2 times a sine of 2 theta. The sine of 2 theta can be written as 2 times a sine of theta times cosine of theta. you just have to perform sine of theta plus theta to arrive in this formula. So we have 9 over 2 theta plus 1 over 2 sine of theta, and this cosine of theta right here we can write as the square root of 1 minus sine squared of theta, using once more the fundamental law of trigonometry. So we have 9 over 2 times theta plus 1 over 2 times sine of theta, square root of 1 minus a sine of squared of theta. Performing again the substitution in the opposite direction, we have theta is equal the inverse function sine minus 1 of y over 3 plus 1 over 2 times sine of theta we write as y over 3 times square root of 1 plus this sine squared of theta we write as y over 3 squared. So we have 9 over 2 times sine minus 1 y over 3 plus y over 6 times square root of 1 minus y squared over 9, and we added a constant right here once we have an indefinite integral. So if we substitute this value in the integral that we call 1 right here, using these integration limits, we have that m could be represented as k times the integral from 0 to 1 of 9 over 2, we are substituting right here, right? Times sine minus 1 y over 3 plus y over 6 times square root of 1 minus y squared over 9, and the limits of integrations of the second integration, remember, is 3x to 3. So substituting these integral limits, we have that m could be right as this 9 over 2, once is constant, could go to outside of the integral. So we have 9 over 2 times k times the integral from 0 to 1 of sine minus 1. We are substituting y as a 3 right here. So we have 3 over 3 plus 3 over 6 times square root of 1 minus 3 squared is 9. So notice that we have 9 over 9 right here. So it's 1 minus 1. So all this term is equal to 0. You can cancel this term right here. And substituting the y as 3x, we have sine minus 1 of 3x over 3 minus 3x over 6 of square root of 1 minus 3x squared is 9x squared over 9. So m is equal 9 over 2 times k times the integral from 0 to 1 of the angle which the sine is equals 1 is p over 2, that's 90 degrees, alright? So the result of sine of minus 1 of 1 is p over 2 minus this term, we already said that is equal 0, so just consider the sine minus 1 of 3x over 3, you can cancel 3 with this 3, you just have sine of minus 1 of x minus 3x over 6 will be represented as uh, just after we put this term outside of the integral, this 3 over 6 will be 1 over 2, and note that we have to consider these two integrations right here. Actually, these 3 integrations right here, we have 3 terms. This one, it's just p over 2 of the integral of dx, so it comes out of the integral. So we have the integral of 0 to 1 of dx minus the integral from 0 to 1 of a sine of minus 1 x dx minus the integral of 1 over 2 dx have to stay inside of the integral once is a variable of integral from 0 to 1 of x times the square root of 1 minus x squared dx. So we call this integral right here of 2 and this integral of 3, and we'll perform the calculations of the indefinite integral of 2 and 3, and after that we'll substitute the results in the equation that we'll call star. So let's perform the integral 2. The integral 2 is the integral of sine of minus 1 of x dx. We will perform the integration by parts right here. So we'll call this term u and this dx dv. If u is equal sine of minus 1 of x, du will be equals to 1 over square root of 1 minus x squared. This is the derivative of sine of minus 1 dx, and once dv is dx, if we apply the integral in both sides, we can conclude that v is equal x. So this integral, applying integral by parts, it's uv. So u is sine minus 1 of x times x, that's v, minus the integral of v du. V is x, and du is the term, this term right here, that you can substitute here. Therefore, we have x times sine minus 1 of x minus the integral of 1 over square root of 1 minus x squared times x dx. Performing another substitution, calling w as 1 minus x squared, if we apply derivative in both sides, we can conclude that dw is equals minus 2x dx. Therefore, if I put these two beneath this term dw, we have minus dw over 2 is equals x dx. So we perform this substitution right here. X times sinus minus x plus this 1 over 2 with this minus sign, I will put outside of the integral. So I have plus 1 over 2 right here. And this term 1 over square root of w, I can write as w to minus 1 over 2 dw. So this term will be equals to x times sine minus 1 of x times 1 over 2 times the integral of w to minus 1 over 2. If I add 1 here, I will have w to 1 over 2 over 1 over 2. I will repeat this term right here. If I pass this term to the front of this term of w to 1.5, I will cancel this 2 with this 2 right here. So I just have the square root of w. Once w to 1 over 2 is the same of square root of w. I will perform the substitution in the opposite direction. So I just have x times sine minus x, and w I will write as 1 minus x squared, and once it's indefinite integral, I will just add a constant right here. So this is the result of the integral 2. This integral 3 can be evaluated using another substitution, as you can see right here. We can write u as 1 minus x squared, and performing the derivative in both sides, we have du equals minus 2x dx. If I put this minus 2 beneath this du, I can write minus du over 2 is equal x dx. So the square root of 1 minus x squared I will write as square root of u, and the x dx I can write as minus du over 2. Therefore, this 1 over 2 with these minus signs I will put outside of the integral, and the square root of u I will write as u to 1 over 2. If I perform this integral right here, I have u to 3 over 2 over 3 over 2. I can cancel these 2 with these 2 right here, and I have minus 1 over 3 times square root of u cubed plus a constant. This u cubed I can split as u squared times u. This u squared I can put outside of the square root, so I have minus 1 over 3 times u times square root of u plus c. This u I will write as 1 minus x squared, so the value of this integral is minus 1 over 3 times 1 minus x squared times square root of 1 minus x squared plus a c. So if we substitute the values of integral 2 and 3 in the start formula of the mass of the solid E, we have 9 over 2 times k times p over 2. The integral of dx is just x, which varies from 0 to 1, so this integral right here is equal to 1, and 1 over p over 2 is just p over 2, minus the value of this integral we already evaluated, so we just use the integration limits 1 and 0. So if we use 1, we have 1 times sine minus 1 of 1 plus 1 minus 1 squared, minus, if we use 0, we have 0 times sine of minus 1 of 0 minus square root of 1 minus 0. That's it. We can see that this term right here will be cancelled once we have 1 minus 1, as well this term right here will be equals 0 2. So we just have p over 2 minus sine minus 1 of 1 plus, once you have minus times minus, plus 1, and we have just to consider the another integral right here, that is the value of the integral 3. Let's see it. The integral 3 we evaluate, here is the value, and we use the limit of integration 1 and 0. If we use 1, we have minus 1 over 3, 1 minus 1, square root of 1 minus 1. So this term right here will be cancelled. This minus with the minus of the formula will result in a plus sign. So you have plus 1 over 3, 1 minus 0 squared, which is 0, times square root of 1 minus 0. So you just have 1 over 3 times 1 over 2. Once you have a minus sign right here, we have minus 1 over 6. So the mass of the solid E is equal to 9 over 2 times K times P over 2 minus sine minus 1 of 1 plus 1 minus 1 over 6. This term right here in the brackets is approximately equals 0.833. If we take this number right here and consider this number times 9 over 2, we have 3.25 times K unit of mass, and this is the mass of the solid E finally. So if you have some question about this exercise, please leave your comments. I will answer you as soon as possible. I'm awaiting your visit in the next videos. Bye.